So here we discuss the derivation of the material derivative. So remember that the material derivative tells us how a quantity psi changes with time or what is the change of psi, so what is delta psi, when we follow a material element. So a function psi is a function of 4 independent variables. So this is x, y, z, and t. Psi could be temperature, so temperature would be a function of 4 independent variables. You can measure temperature at any location in x, y, z, and at any time. And so in terms of mathematics, the mathematical way to look at the variation of a function, if we know how we change x, y, z, and t, is the total differential. So the total differential mathematically describes how the value of our function psi changes when we can vary our variables independently. That means when we can choose a delta x, so a change in x, a change in y, and a change in z, and a change in time independently. And that is the total change in psi is due to the fact that we change time, so we're looking at a later time, is due to the fact that we may have moved a certain delta x, which we choose independently, and we may have moved by a certain delta y, and that we may have moved by a certain delta z. All of our variables are independent, and so we can choose these delta t, delta x, delta y, delta z in principle independently because psi is a function of 4 independent variables. And so from the formula for the total differential, you know how to relate the change of phi to a change in the variables. It's simply d phi dt delta t plus, d psi dt times delta t plus d psi dx partial x, delta x plus partial psi partial y times delta y plus partial psi partial z plus delta z. And now this quantity here really represents the change in psi, which is due to delta t. And the same here, this is the change of psi due to delta x. And again, the same for this term and for that term. All right, so here we have described this change of psi, which is associated with a random step delta t of time, a change of delta x, a change of delta y, and a change of delta z. At this moment, I'm still describing t, x, and y, and z as independent variables. Now, how can we use this if we want to derive the material derivative? So for material derivative, the question is that we want the change of psi, so we want the delta psi. So we want to relate the change in the value of psi. So we want to relate delta psi. Actually, I shouldn't say relate, but more to quantify the change in psi when we follow a material element. Now, how can we say mathematically that we follow a material element? So let's assume these are now, I'm going to assume that these are particle path lines, okay? And that we are following a particular material element. So we follow this particular material element, which is at this position x, at this given time t. So it's hard to represent this in 4 dimensions, because we have now 4 dimensions, but you have to realize that we just said we want to follow material element. That means that this particular material element is now precisely here at x plus delta x, when t is t plus delta t, right? So when I took this step in time, when I said, okay, I want to look at a delta t later, I cannot change delta x independently. I cannot say, well, now I'm going to be here, or I'm going to be here, and vary delta x and delta y independently. Once I say I follow a material derivative, my variables are no longer independent, but if I take a given step in delta t, then the change of position, so the delta x, is fixed. So here, if we follow a material element and look at the change of delta x after a certain delta t, so we follow this material element for a short time delta t, delta x, so the change in position, cannot be chosen independently. It has to follow the flow. And remember, this is here a vector delta x, so this includes the change in the x position, the change in the y position, and the change in the z position. So we have to follow the flow. All right, so then how is delta x, delta y, delta z in this case related to delta t? When we follow a material element? Now the answer is through the local flow velocity. So what we can write is that for a given delta t, if we follow the material element, right, so if we move with the flow, then delta x is going to have to be equal to the local velocity in the u direction times delta t, and delta y is going to have to be the local velocity in the y direction times delta t by definition of the velocity, yeah, and delta z is going to be equal to w times delta t. Yeah? So delta x, delta y, delta z are no longer independent, but they really depend on delta t. Right, so here really I'm simply saying that this displacement here, if I'm following the flow, this displacement delta x is equal to u times delta t, because I'm following the flow. Okay, so then I can rewrite the change in delta psi. I can rewrite this here, but substitute delta x for u delta t, delta y for v delta t, and delta z for w delta t. And now when we write the change in delta psi this way, it becomes immediately apparent that the change in delta psi, if we say that we follow the flow, so if we look at a material derivative, only relates to delta t, to the change in time. So we can factorize this delta t and write now that delta psi only depends on a delta t, right? And we factorize the delta t in this expression. So we get delta psi delta t, partial psi partial t plus u partial psi partial x plus v partial psi partial y plus w partial psi partial z. So here this delta psi represents the change in psi over time delta t when we follow the material element. So if you divide this quantity, if you divide both sides by delta t, here you'll have a delta psi over delta t. So you see that this here looks like a derivative, and that is the material derivative. So this is the material derivative, and we don't write it with deltas, we write it with capital D's. So we write capital D psi, capital D t is equal to partial psi partial t plus u partial psi partial x plus v partial psi partial y plus w partial psi partial z. Now you see here that the three last terms together look like the dot product between the vector u, v, w and the gradient of psi. So another way of writing this is that the material derivative is equal to partial psi partial t plus u dot grad psi. So to recap, psi is a function of independent variables. So in a way, the first way of thinking about the changes of psi would be to look at an Eulerian perspective. How does psi change at a given position? That would be d psi dt. But that is usually not what we want to do when we look at conservation. And so the material derivative precisely gives us an estimate of a change which is more linked to the Lagrangian point of view, and that is how does psi change if we follow a material element. This is the information which is in this number here.